Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 9 academic students who are studying the measurement and geometry unit of the course. This is the first video in the geometry portion of that unit. Now we've been saying geometry, but really the proper name for this is geometric relationships. We just like to use geometry as a short form. As part of this particular part of the unit, we're going to look at angles, polygons, and parallel line systems. Oops. Now let's start by reviewing the very most basic concept for this unit. What is an angle? If I asked you to tell me the difference between these two lines, it's easy to conceive that you would simply measure the distance between them with your ruler. And if you measured here and I measured here, we would get the same value. But what if I asked you the distance between these two lines? Well, if you measured here and I measured here, we would get very different answers. So we don't want to talk about the distance between two lines if those lines share a common point. Because here you could say that their distance is 0, but somewhere way up here you could say their distance might be a meter or 100 meters if those lines continued forever. We don't talk about their distance. Instead, what we talk about is how far away are they turned from each other. So because they're attached at a point or they share a common point, we talk about their turning distance. And that turning distance is measured in something called an angle. So these two lines are a certain number of degrees away from each other, and that's called an angle. Instead of a distance between them, there is an angle between them. And that angle is measured in degrees. How big is 1 degree? Well, that's an important question. So in order to understand what 1 degree is, we actually have to study more than 1 degree. Because when it was decided what a degree meant, they actually didn't decide what 1 degree was, they decided what 360 degrees were first. So if we think about these two lines, they could be 0 degrees away. We don't have to know what a degree is to know that these two lines are 0 degrees away, meaning they're not at all turned from each other because they're on top of each other. So now I'm going to start to turn them away, and you can see that the turning distance gets bigger and bigger and bigger. And if I keep turning and keep turning and keep turning, eventually I come back to where I started from, back to 0 degrees. So that means that there is a maximum angle that you can rotate away from something. So again, I'm going to rotate away, rotate away, rotate away, but I end up coming back to where I was. So that maximum angle is 1 full circle, or to get very fancy with vocabulary, 1 full revolution. So 1 full circle is the basis for how we measure angles. And 1 full circle is an angle of 360 degrees. And this little mark up here, which is kind of messy at the moment, let me see if I can make it nice for you. You know that the way to mark that you have a degree is with an open circle like this. So 360 degrees is 1 full circle. Now, it is kind of interesting as to why it's 360 degrees. It seems like kind of a very strange number. And I agree with you. It's certainly not what I would have picked if I was around in ancient times. But why did they pick 360 degrees, these ancient mathematicians? Well, there's kind of 2 prevailing theories on why that is. The first theory is that ancient mathematicians studying circles, their favorite circle to study, the most important circle for them, is the circle of the Earth orbiting around the sun. That was the most important circle for them. I mean, of course, we now know that it's not really a true circle, but back then, they knew a lot more than we give them credit for. Anyway, that was the most important circle for them, and that circle took 365 days. So that's sort of close to 360. So maybe that had something to do with this particular measurement. Another theory is that a lot of ancient mathematicians, well, primarily a group called the Babylonians, really, really loved the number 60. I like it too, but they loved it so much that it was the basis of their counting system. Just like you and I count on basis 10, and therefore we love numbers like 5 and 10, they loved the number 60. And if you love the number 60, then this number here is a pretty nice number. So maybe, this is what the theory is, maybe these Babylonians who loved the number 60 and knew that there were 365 days in a year kind of combined those ideas together to give us 360 degrees in a full revolution. Well, we'll never know for sure, and you certainly don't have to know all of this interesting history stuff. I just find that it's fascinating, and I love talking about it, obviously. So what do you have to know? You have to know that there's 360 degrees in a full circle. Therefore, half a circle, hey, a straight line, is 180 degrees. And a quarter of a circle is our much beloved 90-degree angle. Okay, so that's what a degree is, and that's how we measure how far something has turned. And I just want to give you a little heads up that you study degrees in grade 9 and 10, but later on you're going to discover, and you probably won't be too happy about it at the time, later on you're going to discover that there are other ways of measuring a turning distance. So degrees is one method, and it is the most common method, but as you get further and further in your math studies, you'll discover that there's other ways of measuring how far you've turned. For now, we only study degrees. So what we know is that angles in a full circle add to 360 degrees, and angles in a straight line, meaning half a circle, add to 180 degrees. So you should be able to solve for x, and you have several different options as to how you do that. So one option is to kind of pick a starting point and say, if I go from here all the way around, I've gone a full circle. So therefore, x plus 50 plus 130 plus 50 plus 95 must add to 360. And you can write that as an equation. X plus 50 plus 130 plus 50 plus 95 is 360 degrees. And you can solve for x in this equation. But again, that's not the only thing you could have noticed. You could have also looked at, for example, this straight line and said, well, in a straight line from here over to here, I've rotated through 180 degrees. And therefore, these angles, 50 plus x plus 95, must add to 180. So 50 plus x plus 95 adds to 180 degrees, and you could solve for x that way. Again, that's not the only thing you could have done. You can also have noticed this straight line and said, well, that straight line means that from here over to here is 180 degrees. And therefore this plus this plus this is 180. So x plus 95 plus 50 is 180 degrees. So let's go ahead and actually do the math. 95 plus 50 is 145. Subtract 145 from both sides, and you get x is 35 degrees. And you would have got that no matter which method you used. Okay. Now, the next important thing in understanding angles is that in a triangle, all of the angles add to 180 degrees. So all of these interior angles, and there's 3 of them, will always add to 180. Now, I don't want to go through the proof of that with you. You should have seen the proof in a previous grade. There are great proofs on the internet. Some of them are written, some of them are animated, and some of them are manipulable. Here's one, for example. So if you really want to see the proof of this idea, then I would say check out the internet. For us, it's important that you simply know that rule, that all the angles in a triangle add to 180. And therefore, if I wanted to find x in this diagram, I can say that x plus 71 plus 43 equals 180, and therefore x plus 114 is 180, and then solving for x, I get 66 degrees. And I'm hoping you learned that in an earlier grade. Same with this. I hope that you learned that in an earlier grade, well, I hope in an earlier grade you learned that the angles in a quadrilateral add to 360 degrees. A quadrilateral is just a four-sided figure. So for example, a rectangle, a parallelogram, a square, a rhombus, a trapezoid, those are all quadrilaterals. And the interior angles of a quadrilateral add to 360. And therefore, if I wanted to solve for x, I could say that x plus 138 plus 60 plus 87 equals 360 degrees. So collecting like terms, 138 plus 60 plus 87. So x plus 285 is equal to 360. So subtracting 285 from both sides, I get x equals 75. You'll notice at no point should you be ever measuring. So for example, some of you might own, let's see if I can find it here. Some of you may own one of these. Just a second, I'm finding a picture of it. You might own one of these, but please do not be tempted to use them. They're probably useful in science class. They're probably useful in math class. Sorry, in art class. But in math class, we don't want to use them because we are not measuring diagrams anymore. In fact, as you can tell, diagrams are not made to scale. I've put 87 degrees on this angle, but in fact, that angle is closer to 110. So don't try measuring angles in high school math. High school math is all about calculation, not measurement. Okay? I want to say one other thing about angles in a quadrilateral, and that's if we have a special quadrilateral called a parallelogram, then of course the angles add to 360, but something else happens too, which makes for a lot of interesting shortcuts, that in a parallelogram, angles add to 360, but it's also true that opposite angles are equal. So this angle and this angle would be the same, and this angle and this angle would be the same. So that's just something to keep in mind, that if you have a quadrilateral that happens to be a lovely parallelogram, then don't forget about this opposite angle trick, that in a parallelogram, opposite angles are the same. And don't forget that a parallelogram includes rectangles, squares, and rhombuses. Okay. Now, here's the guy who always is thinking. He says, so we've looked at four-sided shapes and three-sided shapes, and this guy wants to know, what about five-sided shapes? What about six-sided shapes? Hey, what about 18-sided shapes? Is there a pattern? Well, there is, but this guy here and you are going to have to go to the next video to find out, because we're running out of time in this video and I don't want to have to rush through it. Okay, so that's the end of video number 1 on geometry, and I'll meet you at video 2.